I have rotated my screen now. Let's see if this is better. I'm going to be continuing 9 ASP end of year focused IPQs. I did skip a page here because it's pretty much the same stuff as we've done in the past. So you can give this page a try yourself. I'm going to move on to work done. So in which of the case is the net work positive? It's called network, but it's supposed to be net work. Let's see. Work done to hold this much and walk forward. Okay, so this is not going to be positive work. In fact, it's not even going to be work at all. If I am standing and I am holding a barbell, so I don't know why I've got 4 legs and a long arm. Let's just figure this out. I am holding this barbell, which means I am lifting it up, but I am walking forward. Up and forward, this is perpendicular. Work done is 0 when it's perpendicular. If you need to know the formula, W equals FD cos theta. Cos of 90 is 0. Work done to raise and lower our set. Okay, so raising and lowering to the floor. Doesn't matter how many times you do it, there is no work done because it starts from the bottom, goes up and comes back down. So it cancels each other out. Holding at a constant height, then you're not moving it, so work done is not going to be done. Funnily enough, work is not going to be done. Why? Because I have to move a distance. Work done to kick a set, so I've applied a force, 25 kgs, and cause them to roll, so I'm making them move. So that means this is work done, and it will be positive because I'm moving in the same direction. Work can be negative if it's in the opposite direction. So the force is in the negative direction, the work will be negative. I just mentioned that. For example, friction, which happens to be the next question here. Does friction always do negative work? Actually, well, yes. Because why? Because, that says because, okay? Because it is in the opposite direction of the motion. If I'm moving forward, friction is going backwards. If I'm moving back, friction is going forwards. Is it possible to do work at something that remains at rest? Well, of course, no, it is not possible. No, because you need a distance. You need a force and a distance. So that's the simple way to answer that. So, to solve some problems, we have the mass of a bicycle and a cyclist together is this. How much work has been done if I change the speed? So from here to here. Okay, so of course in this case W equals FD, that's not going to help because I don't have a force and a distance. I also do know W, work done, is the change of kinetic energy. That means kinetic energy final minus KE initial. That's okay. This is what I'm going to use. So it's supposed to be a half mv squared, if you check your formula sheet, minus a half mv squared. This will be final minus initial. But if you're good with math, and to simplify it for you, the half and the m, that's constant anyway. So that's just going to be a half m. Just to make things quicker, I could do v final squared minus v initial squared. That's all I need to do because I'm only changing the speed. I'm not changing the mass or the half. So, in order to solve this, let's put the numbers in. A half times 53 times V final. So I finished at 127 squared minus the starting speed, 3.84 squared. Putting that into your calculator, you should get minus 348 joules. So that will be B. It is minus because it says slowing down, so I am doing work on it. Negative work is being done on it. So let's move on. What is the net work required to accelerate this car to this speed? So we are increasing the speed, so this should be positive, which it is on the options. So it's the same as before. W equals change of kinetic energy. You don't need to write this out every time because it's just multiple choice. But anyway, W equals, I don't know why I wrote W again, I'll just do a half m v final squared minus v initial squared. Putting this into our calculator, a half times 1000 times v final, which is 30 squared minus 20 squared. Putting that into your calculator, you should get 250,000. I believe there's a mistake in the answer key. It's supposed to say A, but that's not true. If you calculate it, you will get 250,000. A 65 kilogram bicyclist rides this with this speed. How much work must be done in order to bring it to a stop? So if we're bringing it to a stop, the final speed will actually end up being 0. So I can do W equals a half m v final squared minus v initial squared equals a half times, well, there's two masses here. We have 65 kg and 8.8 kg. A half mv squared, we have two masses, 65 plus 8.8, which gives you a half times 73.8 squared. My math is amazing, that's how I know that. Multiplied by the change of speed, 0 minus 14 squared. Putting that into your calculator, you should get negative 7200 joules. Now, one of my students has disturbed me, so I'm going to pause this video and I'll continue later. Thank you. Hey, I'm back. Funny thing is, the student that disturbed me was literally asking me these two questions. So I just managed to finish them in time and we fixed the problems. What are we doing now? We're continuing. We are finding the magnitude of the braking force if it comes to a rest in this much time, not this much time, this much distance, that's meters. Okay, so we have a distance, we have a force, and previously we calculated work done. W, F, and D. You can probably guess the formula if you check the formula sheet. FD usually cos theta, but as you can see there's no angle, so no need to write the angle. I'm looking for F, so I will rearrange, or I can do shift solve. It doesn't matter what you do. It's so easy to rearrange, I'm going to do that. W over D. The work, which we have just calculated, is minus 7200 divided by 3.5. 7200 divided by 3.5. Hopefully, the answer should be minus, what will it be? Minus 2100. Now, it did say magnitude, so I don't need the minus. It's not important in grade 9, but by the time you reach grade 12 or grade 11, you will have to deal with that, the minuses. So the final answer will end up simply being the magnitude only. 2100 newtons. That's the final answer. So keep that in mind. If it says magnitude, you don't need the minus. So we have t equals 1 second. This falls with the speed of this. At t equals 2, it has this energy. What is the kinetic energy at t equals 1? So if you want to find the kinetic energy at t equals 1, well, that's simple. That's just the kinetic energy formula, isn't it? Half mv squared equals a half times, we have that distance, not distance, mass, 0.40 multiplied by the starting speed, which was this one here. So that's 6 squared. If I do that, I will hopefully get 7.2 joules. What is the speed at this? So this time they gave me the energy, I need the speed. So Ke equals, again, a half mv squared. You can rearrange the formula or you can do shift solve. Because I rearranged the previous one, I'll continue to rearrange. What you can do is simply v squared. I will take this to the other side. That will become Ke. I can do divide by a half or multiply by 2. I'll just divide by a half m. This is multiplying with the v. I will divide on that side. Equals v squared. But I don't want v squared, do I? I want v. So, to cancel the square, I'll take the square root. That's all. So, v, I'll write it out again, equals square root of my kinetic energy, which we have, 25, over a half multiplied by 0.40. Like I said, you can just put the numbers in the places and you can do shift solve like we've done in the previous questions, but I thought I will change things around this time. And if you do that correctly, hopefully you get 11 meters per second is fine. How much work was done? So work done, as we've done previously, W is the same as the change in kinetic energy, right? So change in kinetic energy, that will simply be Ke final minus Ke initial. And let's do it. What's Ke final? The final speed was, not speed, the final energy was 25. So 25 minus the starting energy, which was already solved right here, 7.2. 25 minus 7.2, let's just check, 25 minus 7.2, and you will get exactly, the calculator's not even on, that doesn't help. 25 minus 7.2, calculator is now on, 17.8 joules. 17.8 joules. Very good. moving on. Potential energy. What's this? What is potential energy? Energy of motion? No, that is actually kinetic energy. Energy transferred through heat? Well, no, that's just heat energy. Chemical reactions? That's chemical energy. Stored due to a position? Yes, due to a position, like height, for example, gravitational potential energy, or even elastic potential energy when you have like a rubber band or a spring. So this is stored energy. Potential basically means, why did I draw a line through it? Potential simply means stored. So this word here is stored energy. Okay, which of the following has gravitational potential energy? Laying flat on the ground? No, because you want to be raised off a height. Anything at a height, you need H. Why, I hear you ask? Because potential energy is not a half mv squared, it's mgh. I need a height, usually. A car moving on a flat road, again, he's on the road. The car on the road or the book on the road, I don't know why they're the same size. That is not good. These are not good. Rock held at a height, there we go. There's a rock, funnily enough. I drew a rock and it's at a height. This is nice. Rolling in a football field? No, because again, it's on the ground and it's rolling. That will have a kinetic energy, but it will not have a stored energy. Okay. Which of the following processes is due to transfer of collisions between particles? Due to collisions. So we're moving over to the conduction, induction, radiation stuff. Conduction means particles bump into each other. They hit each other and the energy gets transferred by them vibrating and moving along. That's conduction. Induction is without touching, by the way. The particles don't touch with each other. Radiation is like a wave of energy, which also is not touching either. Fusion is when particles collide together and create energy. It's nuclear fusion, for example, turning into radiation. We're not going to deal with these two things. It's not important. Well, that's important, but this is not important right now. We will do latent heat of fusion later, but for now, this is not for conduction. Moving on. Thermal energy or thermal exchange process carries energy through boiling water. Boiling water is when the particles are moving around inside maybe a water container. The particles move around. They get hot, they go up, they get cool, they come back down, and they keep going up and down in a little circular motion. Not circular, but in a little motion like this. That is called convection. So, conduction is when particles bump into each other. Convection is when the particles themselves move around the area. Radiation, as we mentioned, is a wave of energy, and the particles actually don't move. The energy is a wave that travels. Evaporation is when the top layer of the surface turns into a gas. Like water evaporates into steam or gas, only the top layer. Boiling would be the whole thing. Okay. Which of this requires no medium? I just mentioned it. Particles don't move in radiation. They don't move in radiation. Thermal energy is transferred when objects touch each other. As I've mentioned, conduction. Which heat transfer is responsible transfer for energy from the sun to us? Well, the sun is in space, right? A big giant sun in space. We have Earth over here. The energy comes through, there is no particles in space, so it's a vacuum. So in order for us to get the sun's energy and get happy, we will have to use radiation. Very nice. The specific heat of a substance is the amount of heat required to do what? To change the something of 1 kilogram by something. Okay, so specific heat is basically if you have 1 kg, right? So this is an object and that's 1 kg, and I put it on a stand. This is a stand. There's a bit of chemistry going on now. Here is a Bunsen burner, maybe, like a little fire. I'm going to heat this up. I want to raise the temperature of this by 1 degree. 1 degree Celsius or Kelvin. It doesn't matter because you see Kelvin here, but down here it's got Celsius. Both are fine. It's the same difference. So what am I doing? I'm increasing the temperature. Maybe it's already at 20. I want to know how much energy I need. To find the change to get it to 21 degrees. If I want to go from 20 to 21, for example, it could be anything. 1 degree change. How much energy is required for 1 kilogram? Some objects are more dense than others. If I place another object here, and this is also 1 kg, but it is very dense. It has a high heat capacity, for example. It will take longer or more energy to do it. So that means I can find the difference. So let's get back to the question now. Amount of heat required to change 1 kilogram of the substance, the temperature by 1 degree. Yes, yes, yes. Not state. And I don't want to change the state. I don't want to boil it. I don't want to freeze it. I don't want to change the state. That is a different type of energy. That's latent heat. Not specific, that will be latent. So no change in state. All right. A hot metal of this mass loses this much energy as its temperature drops by this much. What is the specific heat capacity of the metal? So if you want to know the specific heat capacity formula, it is Q equals Cm change of temperature. We have the change, we have the mass. Oh, that's grams. That's not good. Let's convert that. We must divide that by 1000 to put it into kilograms. Because you see here it's kilograms, kilograms, kilograms. And joules. Good. Rearranging, shift solving. I did rearranging earlier, so I will continue. So I'm going to take all of this, I'm going to take it to the other side. It'll be Q divided by M change of temperature equals C. Let's write it over here now, continuing on. Q, what is it? 3500 divided by the mass, so 0.05, that's 50, I'm dividing by 1000, multiply that by the change of temperature, 110. Don't need to convert to Kelvin because this is also Celsius, so I don't need to convert to Kelvin. If you did, you just add 273, but no need. So let's do that in the calculator. Let's put the little thing here, 3500 divided by 0.05, multiply that by 110, and I will get an answer of 636 joules. So C is correct. Very nice. And what I'm going to do is I'm going to stop there for this video because it's going to get too long, and I'll continue in the next lesson. Thank you.